Think about this. Even an elephant with its massive body can float when it enters water. So, how can something so heavy be held up instead of sinking down? Well, the secret lies in an invisible upward force, and that's exactly what we are about to uncover in this lesson. So, what we have here is a thin plastic sack completely filled with water and submerged in a larger body of water. And what we see is that this sack is in static equilibrium. In other words, the sack stays in its place, neither sinking nor rising. That means the gravitational force Fg on this sack is balanced by a net force that acts upwards due to the water surrounding the sack. And where does this force come from? That is this one. So recall, there is pressure acting at every depth, and that, when we multiply by the area it acts on, results in force. Now, this net upward force has a special name, that is the buoyant force. So, you know that the force on the sack at a lower depth would be greater in magnitude near the bottom than at the top, simply because pressure increases with depth. And this is the reason that the force vectors drawn around the bottom are longer in length than those shown here at the top. Now, if we add all the forces vectorially, the horizontal components will cancel. But the vertical components will add up to give a net buoyant force that acts upwards on the sack. So what we see is that since the water sack here is in static equilibrium, the buoyant force must exactly equal the weight mg of the water sack. And here the subscript F reminds us that this is the mass of the fluid inside the sack, that is water in this case. So from this equation, we can say that the magnitude of the buoyant force is equal to the weight of the water in this sack. Now, what we'll do is put a stone of exactly the same shape as that of the sack in place of the water, such that it exactly fills the same space. So you could say that the stone has displaced the volume of water that was earlier in this space. And here is a crucial point. The surrounding water doesn't care whether that space is filled with water, stone, or anything else. The forces on the surface depend only on the displaced volume, and so the same buoyant force that acted on the water sack now acts on the stone, that is this, or the weight of the water displaced by it. But the difference here is that the stone will not be in static equilibrium like the water sack. And the reason for it is, we know the stone is much heavier. But in the language of physics, we say that now the downward gravitational force on the stone is greater than the magnitude of the upward buoyant force on it. And as a result, the net force points downwards, and the stone therefore accelerates towards the bottom. Now, let's do one more variation where we replace the stone with a block of wood of the same shape. And just like before, we know that the surrounding water exerts the same buoyant force equal to this, or the weight of the water displaced by this piece of wood. But this time, we see the situation flips. That is, the gravitational force on the wood is less than the buoyant force. That means the net force points upward. So the block of wood accelerates towards the surface. And this is precisely the reason why wooden logs, ice cubes, and even ships float, because the weight is less than the buoyant push of the water they displace. So in all these cases, that is the sack, the stone, the wood, the behavior can be summed up in a single powerful rule known as Archimedes' principle that says whenever a body is immersed in a fluid, either fully or partially, it experiences an upward force called the buoyant force. And the magnitude of this force is equal to the weight of the fluid displaced by the body. So, to make this absolutely clear, when I say a body is partially immersed, for example, if a block of wood is 40% submerged in water, then only that 40% of its volume counts towards the displaced water. In other words, the buoyant force comes from the weight of just that displaced portion, not the entire block. Another important thing to note is that this is the mass of the fluid displaced by the body and not the mass of the body itself. And this distinction is what often confuses students. So you must keep this in mind. Okay, now let us understand what really happens when a block of wood is put in water, as in how the force dynamics change as the block settles into equilibrium position. So let's place a wooden block gently on the surface of water. At first, gravity pulls it downwards, so the block begins to sink a little, and as it sinks, it pushes aside or displaces more and more water. According to Archimedes' principle, the more water displaced, the greater the upward buoyant force acting on the block. Eventually, the buoyant force grows till it exactly balances the block's weight, and at that point, equilibrium is reached. The block stops sinking any further and simply floats. So in general, whenever a body floats in a fluid, the buoyant force FB acting upward is always exactly equal in magnitude to the gravitational force Fg acting downward. Now, from Archimedes' principle, the buoyant force Fb is equal to the mass of the displaced fluid into g, and so at equilibrium, force of gravity on the block is equal to the mass of the displaced fluid into g. In other words, if a body floats, its weight is exactly equal to the weight of the fluid it displaces. And that's the golden rule in flotation. Whether it's a tiny cork, an ice cube, or a massive ship, if it floats, it must be displacing its own weight of water. So the next time you see a boat gliding, remember you are witnessing Archimedes' principle in action. It's a reminder that even the heaviest things can be supported as long as they find the right balance with nature. And that's the beauty of physics. It reveals the hidden simplicity behind what looks like magic.